Welcome back to part 3 of lecture 1 on introduction and digital hardware. So what I want to do in this final part of lecture 1 is to give you a few examples of some specific work that's been done, just to give you an indication of what might be done, achieved using evolvable hardware. So first of all, let's look at an FPGA system that was created actually in the department. This one was done, and in fact it uses CGP, so Cartesian genetic programming, as the evolutionary algorithm, and it uses an FPGA system as the evolvable hardware. Okay, and obviously it's not actually a fully embedded system in that this board is connected to a PC, and in fact the CGP algorithm is running on the PC. Rather than actually on the FPGA. Although there's no reason these days, with the size of the FPGAs and the power of FPGAs, computational power of FPGAs, why you couldn't run some evolutionary algorithms actually on the hardware as well. So you'd actually have a fully compact system. But in this case, it wasn't. It was run on the PC. Okay, so the evolution itself, though, is undertaken on the hardware. So it's not simulations of the genomes. It's actually the genomes are downloaded on the FPGA, and the behavior of that particular circuit is run on the FPGA and evaluated on the FPGA. Okay, so let's look at the structure that we're talking about. So if you remember the last part of lecture 1, I was talking about creating a virtual cell structure on top of the FPGA fabric to allow us to do evolution. So in this case, we've got something here that looks very similar to what I was talking about in the previous part, where we've got a series of cells. We'll see in a minute what these cells look like in some detail. Okay, and they've got connections back, and again, in fact, in this architecture, they're back two columns. They go back to 2 columns. So the first column just has inputs connected to it. The second column has inputs and the outputs from column 1, etc. As we go down, and we've got an output at the end here. And this particular application was looking at image filtering. So the input to the hardware was in fact a 3x3 grid, which was part of an image. It was taken part of an image, and of course it's scanned across the image as it was doing the filtering, and so that was the initial input into the system. And what we were looking at the filter to do was actually filter out noise on the image. Okay, so we'll see examples of that and comparing it with more traditional filtering as we go on. But first of all, let's look in some detail of what this structure looks like. So here we go. So we've got the input data as we've got here, and rather simply to do the identification within CGP, we need effectively every input, and then once we're in the cell, every output to be numbered. So what you'll see is the inputs are from 0 to 8. Okay, remember it's a 3x3 block that we're inputting, so that's 8, and then the output of this cell is 9, this one 10, etc. So 10, 11, 12, 16, up to 32. Okay, up to output number 32, and this just simply allows us to do an identification in the CGP system of later on what inputs are these, and we can number that they're related to these numbers that we go from as we go through the system. Okay, and the bus size is obviously related to the number of bits that go, and how big the bus needs to be to carry those bits through. Okay, so in each column we've got 4 processing elements. Okay, as we go through the system. Okay, so let's look in a bit more detail at each of the processing elements. So in this particular case, we've got our functional block, and which, remember from part 2 of the lecture, is effectively implemented as a RAM, as a lookup table. and we've got two inputs. So in this case, two multiplexers. Okay, and each multiplexer has got inputs from 0 to n to choose from, 8 bits wide, which then go through to the functional block. And so what the evolution plays with, what the evolution has got a handle on, are the configuration of both the multiplexers. So configuration G1 configures multiplexer 1, configuration G2 configures multiplexer 2, configuration G3 configures the function that we've got in there. And of course, these make up one small part of the whole genome that evolution is playing with. Okay, so if we look at the functional code, so remember inside here, we've got a functional block. So what functions have we got to play with? Well, we initially, because it was specific to doing image filtering, we looked at a number of functions. And remember, we've got two inputs, an X and a Y input into this block. So what arithmetic functions, logic functions, sorry, could we do within the functional block? So we looked at 16 possible ones, and actually what we found was there were only really 4 of them that proved to be useful for evolution. So ones that evolution chose often that gave pretty good results. Okay, so F5, F7, F8, and F13 in this set. Okay. So actually, we decided in this particular case to only choose those 4 functions. So 1, 2, 3, 4. So they were the functions that the functional block could choose from. We decided that it just was a waste of time to give it a broader set. It didn't really do that. Okay, and obviously the X and Y inputs are the inputs for multiplexer 1 and multiplexer 2, as I said before, that go into the functional block. Okay, so let's just see how the chromosome was encoded. So remember, this is our full system, and this is an example of a chromosome here. And what you'll see is it's in blocks of 3 digits. It's in blocks of 3 digits. Okay, and if you remember with CGP, and with this, and so this configuration here matches very nicely with CGP, where it talks about the inputs and the function. So we've got 3 digits here which represent our 3 control bits, which affect the inputs that are going through to the functional block and the function that's going on within the functional block. Excuse me. So if we look at this, we're looking actually at the gene for processing element 14. So if you look at this, we've got 1, 2, 3, 4, 5. So it's the 6th part of the chromosome. And if we look at that, 1, 2, 3, 4, 5, 6. So we're looking at this processing element. Remember, it's not 6 because we have to include the inputs. So it's actually, the processing elements actually start at 9. So it's this processing element here. Okay, so, and the chromosome associated with its control bits are 12, 1, and 1. So what does that mean? So 12 says, so the first multiplexer input, which is going to the processing element, comes from element 12, output 12, which is there. So it's actually coming, the output of that processing element is the first input to the processing block. The second number represents the second input, which in this case is a 1. So it actually comes from straight from the input data, so without any pre-processing. So Y is input data input 1, and X comes from the output of that processing element there. Okay, and then the final part of the digits is actually the function that this is performing. So it's got function 1, which on our table here is this function here. Okay, so that's it. So So it's doing that function on those two inputs, and those two inputs are coming from those two sources. So each of these 3 digits represents how each one of these is configured, the first 2 digits, and what function it's doing, the 3rd digit. And of course, what the evolutionary loop does is that it changes randomly each of these digits after taking the best parents from the previous generation to create the next generation, and going around the loop in that way. Okay, so just a bit of detail about the actual evolutionary program. So we set it up with 16 individuals running on the hardware. The initial population was generated randomly. Quite often with the evolutionary programs, you can actually seed it so that you're starting off with something that isn't completely random, but in this particular case, we did it as a random generation. Okay, individuals with the highest fitness were selected as parents for the next generation, as templates for the next generation. Okay, and then they had adaptive mutation performed on them to create new individuals for the next generation. So here's some results. So this was the original image, which you can see is really rather tidy. Okay, and then what we did was we applied Gaussian noise to that image. So that's this picture here. So you can see it's nowhere near as clear. That's the first image. And then we applied 3 standard filtering techniques that are used. So mean filtering, median filtering, and Gaussian filtering. And what you can see is that they all somewhat improve this to some regards or another. And then this last block here is the output from our evolve filter. Okay, so it's nowhere near perfect. Of course, it's not perfect, but actually, if you compare it to the ones that are often used, it actually performs quite well. You know? So this was completely autonomous. That the results it came up with were done through the evolutionary loop. Okay, what you'll find with all of them is that where they're lacking is fine detail, like on the feathers on the hat. They all become rather blurred, and this one does as well. But actually, the performance of this was we were quite happy with it. Actually, it's pretty good compared to more standard techniques. Okay, so I want to really finish off now with a final example, which is slightly away from what we've been talking about. And this is a simple robot example. So before I start the video, so this is a video, let me just explain what the screen looks like. So obviously down here, we've got a small robot. It's connected to the computer for power and signals here. And what we've got is the controller on this robot is made up of 6 cells, similar to the ones we were just showing on the FPGA. So each one of these is a computational cell, which allows the control of the robot. Over here, we've got a control panel, which in the initial phase, you'll see when the video starts, the robot's in a learning phase. And that's simply so that the system that detects faults is learning good behavior, which then allows it to identify when it thinks things are going wrong. But in this particular case, actually that it's getting too close to a wall and it's not turning. And therefore the behavior is something wrong here. I better look at doing something. What we've got here are 2 buttons, which through the video you will see, and I'll point out as it goes on. So the first one injects a fault into the function of the controller that's controlling the robot. And the second one injects a fault into the routing that's going on within these cells. And what you'll see is the routing is a more severe case of inducing a fault than just the function. What you'll see on here, as I said, are 6 cells, and you'll see them changing color as the faults are injected, and it needs to reconfigure the system autonomously because a fault has occurred. So let me start the video. So what you'll see at the moment, it's in a learning phase, so that's green. Now it's no longer learning. So you'll see the robot down here is missing walls. So it's not meant to bump into things. What you'll see now is that a function fault is injected. Everything is fine. It gets too near a wall and the system reconfigures. So 2 of the cells reconfigure and it carries on doing this. The next example, you'll see the routing is clicked. And what you'll see is it needs to do a double reconfiguration to carry on working. So here's the fault, gets too near a wall, and you'll see it reconfigures, still not working, reconfigures again. And just as a final example, this is out without any reconfiguration. When a fault is induced, the robot just hit things. Okay, so you'll have to take my word that we didn't inject those faults, but we did. Okay, so this is the end of part 3 and then end of lecture 1. So what we've done is introduced the concept of evolvable hardware, some of the techniques in the evolvable hardware, and look mainly of how we might apply it to digital electronics, digital systems. And in that, I've actually thrown in a couple of robotic examples as well. And we'll see a bit more about robotics in lecture 3 of this series. So just to finish off, there's a couple more papers that you may want to read, focused on. So this first paper is actually focused on the example I showed you on the digital filter. And so some things to think about before lecture 2 in this series. So we've looked at digital devices and how evolvable hardware might work, but what sort of analog devices are you aware of, if you're aware of any, that you think we could be suitable for evolvable hardware? And if you can't think of any, then what functionality might we need to do it on analog? And then the second thing to think about before the next lecture is how might that be useful? So how might that be useful in analog devices? Okay, so that's the end of part 3 and indeed lecture 1. So we'll move on to lecture 2 in the next session. Okay, thanks very much.